So, we come back to our customary drawing with which we begin every lecture, every day, which will continue for some time till I switch over to another topic. And I am dealing with real valued case because I was halfway through some analysis. Last time we are analyzing this error epsilon square n is equal to this, okay, and this is found to be the minimum plus an extra component that I am coming to. What is the minimum? Minimum is when, that is if you consider EON as dn minus the optimal filter transpose xn vector, that is when you use the optimal filter, then the error is EON. Epsilon mean, in fact, I will write epsilon square to be in conformity with the notation. It is this, okay. That is, I want the filters to be ideally the optimal filter, so that En has variance equal to epsilon mean, but unfortunately we do not get that, as I told you, because in that steepest descent derivation we did not replace R and P by their exact values, but by an approximate value, and that is why the convergence takes place in mean. The weights do not converge on the actual optimal filter, but it dances around that in the steady state. So, obviously, the En in the steady state will not be having variance as low as epsilon square mean, but will be having some extra component, and that our analysis showed to be something like this, y equal to 1 or 0, possibly 0 to n lambda I k prime I n. Now, let us define things, redefine, I mean just for our recapitulation point of view. We had R matrix was the input autocorrelation matrix, all input and xn and dn, they are 0 mean, these are all standard stuff. And then we had R equal to T d T transpose, T consists of orthonormal eigenvectors, D the corresponding eigenvalues. R is assumed to be positive definite, which means eigenvalues are not only real, they are also positive, and T d T transpose, T is a unitary matrix, T T transpose is equal to T transpose T is equal to I, that is T transpose is the inverse of T and vice versa, all that we know. Okay. Then we had delta n, our main purpose was to see this, I mean we define this delta n, you remember what is the what does delta n mean? It is the deviation of W n from W opt. Okay. K n was, this side I am keeping a kind of dictionary for our usage. Okay. This is K n is okay. K n is E, this is the, we can say, covariance matrix of the tap weight error or tap error or weight error covariance matrix or correlation covariance matrix, okay. Because delta you are taking is called in the steady state delta n has 0 mean, as you have seen. So, correlation and covariance would be the same. Nevertheless, it is called weight error, delta n is weight error, it is called weight error covariance matrix. Then from delta n we defined for analysis another transform vector, which is T transpose delta n. You remember this delta n transpose delta prime n, which is a vector, this had a diagonal correlation matrix or covariance matrix. That is, if you that k prime not sorry, this is not diagonal, not this is not diagonal, sorry, I made a miss. This what is k prime n? K prime n was, if you really replace delta n by this thing here, what is k prime n? K prime n is E of delta prime n, let's delta prime transpose n, isn't it? And the delta prime n, if you replace here, you will get T transpose k n T. This is not diagonal, but if you define another thing x prime n as T transpose x n, then the components of x prime n will be uncorrelated. If you see its correlation matrix, that will be diagonal, which is equal to D, that we have seen, that is E of x prime n transpose n. If you really replace T transpose x, x transpose T, x x transpose is R, T transpose R T, T transpose R T will be D. So, component of x prime n, they are uncorrelated, they have got a diagonal correlation matrix. This is our dictionary of definitions. Okay. And this k I prime n is comes here along with the ith eigenvalue. Okay. So, obviously, if this quantity, this is the quantity at nth index, at any nth index, the net mean square value of the error is not epsilon square mean, but something more, which is this, and k I prime n is the ith diagonal entry of this transformed covariance matrix at index n multiplied by lambda I. So, with time n, we have to make sure that this quantity remains bounded, that is, if you take the limit of this quantity as n tends to infinity, this should not grow with n, this should remain bounded, and the bound should be in our control by some parameter by which we can keep this as low as possible. Okay. Then our job will be done. Okay. Epsilon square n can never be epsilon square mean, but then they can be made close to each other, at least epsilon square will be within some finite bound, finite limit of finite range from epsilon square mean. Okay. This is what we have to do. So, that means we need to analyze this. This is where we stopped last time. Okay. This analysis is a very lengthy analysis and you have to carry it out, but I have now formed the background by which you can easily appreciate many steps. Only one background I have to form, that I do now. Suppose, forget all this now, suppose I have got a vector x consists of elements say x 1, x 2 dot 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 say x capital L, L number of random variables, maybe 0 mean random variable you can assume to make life simple. Okay. And it is said, or you need not assume to be 0 mean. Okay. It is said that they are jointly Gaussian, they are jointly Gaussian with some mean m. That means, if you take expected value of x, that is E of x 1, E of x 2 dot 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 E of x L, you form a vector of means, and that you call m, this is called the mean vector, and E of x minus m transpose, that is a covariance matrix. So, these are repetitions, this all these definitions I gave in the very beginning of this semester. This you can call sigma, okay, covariance matrix. In the special case where m equal to 0, the 0 mean random variables, sigma is nothing but correlation matrix, correlation covariance matrix, they are same then. Suppose this is given and you want to transform x vector to another vector x prime linearly, that is x prime is some t matrix times a square matrix t, t is L cross L times of your choice times x. Then firstly x prime also will consist of random elements, after all they are coming from x 1, x 2 up to x L. What is, if I call it m x, if I call it sigma x x, what is m x prime? That is E of x prime, apply E over this linear combination, you can take the matrix out, you can directly apply E over this, isn't it? Linearly combining the elements will be summation something times x 1 plus something times x 2 dot dot, then expectation operation. Better you take the expectation on the elements of x and then you will get the same thing. So, it will be nothing but t into E of x, and E of x is m x. So, m x prime is t m x, And what is sigma x x prime? That will be your x prime minus m x prime, x prime minus m x prime transpose, right? Isn't it? You replace x prime by t x, m x prime by t m x, so and so. Obviously, you can see you will get this to be t times sigma x x t transpose, isn't it? You replace this t x, t m x, t out, here also t, but t gets transposed, so comes to right hand side. So, irrespective of whether they are Gaussian or any other, I mean, irrespective of their probability density, joint probability density, this is always true, that if x is a random vector with this kind of mean and this kind of covariance, then after being linearly transformed to another vector x prime, their new mean vector and correlation covariance matrix, they are like this. This is always true, irrespective of the probability distribution or probability joint probability density of these elements x 1 to x l, right. Now, assume that these to be Gaussian, a set of jointly Gaussian variables are linearly transformed to yield another set of variables x prime. Then this results I cannot prove here, because this is if you take a book on probability theory by Papoulis or some other book, you will see these are basic results, but there is no scope to prove here. Some of the things you have to accept, that in the Gaussian is so beautiful, you know, in the case of Gaussian distribution, joint Gaussian distribution, that is if you have a vector x of jointly, I mean random variables which are having a joint Gaussian density, joint probability density which is Gaussian, then if you linearly transform it, x prime also will consist of a set of random variables which are jointly Gaussian. This is a basic result. Okay. So, if x is consisting of jointly Gaussian variables, so will be x prime. But you remember that a joint Gaussian density needed only two parameters, one is the mean vector, another is the covariance matrix, right. This m x and like this was the formula 2 pi to the power l by 2, l number of variables were there, into determinant of that covariance matrix times square root, I think, sigma x x into e to the power minus x minus m x transpose sigma x x inverse 1 by, there is 1 by 2 here. These are definition. Now, my claim is that if you have x prime as t x, then the x prime also will have a similar density function. Sigma x x prime there will be replaced by, can be obtained easily from sigma x by the previous formula, or same here. Some other nice thing you can see, that if T is a unitary matrix, suppose T is a unitary matrix, just as a deviation, suppose T is unitary, then that is suppose x, you find out the correlation matrix of x, R matrix, decompose at T G T transpose, T is a unitary matrix, pick up that T, T x is x prime say. Okay. In that case, determinant of, here we will have sigma x x prime, isn't it, sigma x x prime for the new here. But what is you understand what I am saying, the joint density for the elements of x prime, that will involve which term, determinant of sigma x x prime, right. But sigma x x prime will be what, determinant of T which is T inverse, and this is called similarity transformation. Determinant will be same as the determinant of the original matrix. So, this value and this value will not change. Okay, because T is unitary, this T transpose is same as T inverse. And here when the inverse comes, inverse of this will be what? You will have another term, na? Sigma x prime inverse, that will be what? Replace sigma x prime by this, take the inverse. So, T transpose inverse will come first, T transpose inverse is T. This will come. I mean, I do not need this for our analysis, it is just something I am telling you off the cuff. Okay. But the basic result is there, that if you have a set of Gaussian distributed vector, if you have a vector consisting of jointly Gaussian random variables, then if you linearly transform them, the resulting elements also are jointly Gaussian. That is a basic result. It can be proved, but then it will require some other theorem and all that. I have no time. The proof is not difficult to read. Actually, if you see any probability book, say the book by Papoulis, you will see you first start with transformation of random variable, that is given a random variable x with some kind of density. If you now consider a function f of x, call it y, what will be the probability density of y as a function of y? Not as a function of x, as a function of y, and then you generalize it to not from x to y, but a set of variable x1 to xl to a set of variable y1 to yl. And there it's not difficult, it's given in books, you have to read the several theorems and results, but the Gaussian thing will comes back as Gaussian. Okay. Fine. Now, for this analysis, now I have to basically see the behavior of this guy with time. This is my target now. I have to see the behavior of this guy with time, which means I have to tackle this matrix. It's better I start with this matrix. After all, this matrix, what are these elements? They are the diagonal entries of this matrix, isn't it? I diagonal entry is this of this matrix is this. So, let me rather try to track this guy, how this guy behaves with time as n tends to infinity. From that, I will find out how its diagonal elements behave with time, right. So, let me stop tackling the diagonal elements, let me rather tackle the entire matrix, take care of the entire matrix. Let me see how it behaves with time as n tends to infinity. Okay. Now, if that be, and once again, our mode of analysis is what? Like in the convergence of elements, what we have seen, we first defined delta n, then found a recursive equation of delta n plus 1 in terms of delta n, and that gave rise to some condition on mu, under which norm square of delta n was tending to 0. Here also I will try to develop a recursive equation involving this matrix, or rather the diagonal elements of the matrix. That is, what will be the values of these elements at n plus 1th index, giving their values at nth index, and then I will study the recursion and see how it goes as time tends to infinity. That will be my approach. But to go there, it will take many steps. Okay, but maybe we can then work on fast, because we have given the background. For that analysis, I will make one assumption, another assumption, not only independence assumption is always there for this analysis also, that is, current weight vector Wn is statistically independent of Dn and Xn vector, that is always there. We will be further assuming that Dn and the elements of Xn, they form, or at least elements of the vector Xn, they form a set of jointly Gaussian variables, jointly Gaussian. I will assume probably they are all random, there is some correlation between Dn and Xn, that is why I am trying to estimate it. Okay. We will make the assumption that their joint density between whom? Dn and the components of the Xn vector, that is Xn, Xn minus 1, Xn minus 2, Xn minus capital N plus 1, or Xn minus capital N. That is a jointly Gaussian vector. The vector consists of those variables which are jointly Gaussian. This is an assumption we will make, and which this is a fine assumption, because Gaussian assumptions usually work in practice. This is an extra assumption. Anyway, so let us. So I told you I want to track this matrix K prime n, and what is K prime n? It is the covariance of this guy, or correlation of this guy rather, delta prime n. And what is delta prime n? T transpose delta n. So let us see what is delta n. We know delta n was actual weight minus the deviation, right? Fine. And we knew W n plus 1 is by the LMS. This part we have already done. Okay, I am dealing with purely real valued case. Extension to complex cases exist, but that is much more complicated, no point. So, if you subtract both sides, if you subtract W opt from both sides, you will obviously get delta n plus 1 as delta n plus mu x n E n, and E n is d n minus W transpose n x n. This part is common, we have done this analysis isn't it? This part is the n, W n, you replace W n as W opt plus delta here. Okay. Then if you take the W opt transpose x n, d n minus that will be the optimal error E O n. See, if you replace W n by this plus this, there are two terms coming out of it. One is W opt transpose x n, d n minus that will be the E O n. Another is minus delta transpose x n. Okay. Instead of W transpose x n, permit me to write it in the other way, x transpose n W n. Both are same, under real case at least both are same. So, W n I will replace by W opt plus delta n, x transpose W opt d n minus that will be your E O n, right, and there is another term x transpose n delta n, right. So, I have got delta n, then mu x n x transpose n delta n. Can I skip the intermediate step? We can see possibly. I identity matrix delta n, I into delta n will give you this. Okay, I into delta n, so that is taken care of. There is another delta n coming here, x transpose n delta n, and before that mu x n. So, mu x n x transpose n delta n, x transpose is a matrix and minus sign. So, minus mu x n x transpose n, that is the matrix, that times delta n coming out of W n, and the other term is, if you put W opt here, d n minus this part is the E O n. So, mu x n E O n. Okay. But as I told you, I am not interested in this here. I have got here, we have got k I prime n. K I prime n comes from k prime n. K prime n comes from delta prime n. Delta prime n comes from T transpose delta n, where T transpose came out of the factorization of R. This is called factorization of R. Okay, factorization of a product. I mean, like there are 3 factor matrices multiplied give you this. Okay. So, this T transpose. So, that means delta n is not enough. I have to take T transpose delta n, find out this, then the correlation of that I have to do for n plus 1th index and write that entire thing in terms of its value at nth index. Okay. So, that means delta n plus 1 is not enough. I have to multiply this by T transpose. Okay. This is my, so I have to multiply here also, and I defined T transpose delta n is my delta prime n. You remember, delta prime n is the quantity of interest here. I have to take the covariance matrix of that and the ith diagonal entry. That is why you forget delta n, get into delta prime n. But if you have this, that means what is delta n? T transpose, you take it on this side, inverse of that, inverse is T only. T transpose is unitary, T transpose is, isn't it? Okay. So, here I am multiplying from left hand side by T transpose. So, T transpose will come here, this thing, this entire thing come here, but delta n I will write as T into delta prime n, okay, minus again mu, I multiplied from left by T transpose. So, I have to multiply this also by T transpose, and E O n is a scalar, it remains as it is. This quantity by my definition is x prime n. You remember, I defined delta prime and also x prime. X prime n was T transpose x n, and what is the covariance matrix of x prime n? That was diagonal D. Okay. By T transpose, I developed 2 vectors, delta prime n and x prime n. Delta prime n from delta n, x prime n from x n. Delta prime n, because I am interested in the covariance matrix of delta prime n, not delta n, because the matrix that was coming into operation there was delta prime k prime n here, and therefore here, not k, but k prime. K prime comes from delta prime, that is why I am getting into delta prime, and delta prime is this. but similarly I am using this also T transpose X n, and this has diagonal correlation matrix D coming from R, eigenvalues of R. Okay. And now you see T transpose first element here is I, and then T transpose I T is I only. You replace this here, the first term is I, T transpose I into T transpose T, that is I. So, that is equal to I only, and T transpose, forget the mu, T transpose X n, that is X prime n, and X transpose n T, that is X transpose T, that is same as this. If you take the transpose of this, you do not get X transpose T. So, that time delta prime n, okay, minus mu, this is as it is E O n. I want to find out k prime n plus 1, that is covariance of this. Mind you, this is a very lengthy analysis, very lengthy. We have not done anything here now so far, but this will give you some idea about how to carry out this analysis, how to make some assumption to make life simpler. That will be a good exercise. What I told in the beginning, that I will study the matrix k prime n in a recursive manner. K prime n plus 1 will be evaluated as a in a recursive manner in terms of k prime n and others. That is why I formed delta prime n plus 1 in terms of delta prime n and something else. Then I am finding the the covariance of that, this into its transpose, that is k prime n plus 1. Here I will replace delta prime n plus 1 by this entire thing here also. So, you understand how big that product will be, 3 terms, 9 terms, and I have to analyze each of that. Is why it is very messy, but many things will become 0 by your clever manipulations. But you understand, 9 terms I have to handle. Okay. So, this is very important. So, I will consider all the 9 terms one by one. First is, you remember delta prime n, please see this, you should not make any mistake. There is always a chance of making silly mistake here. Delta prime n plus 1 here, that means no transposition on this, but the next one is delta prime with transpose. So, this and the same thing, but every term will be transpose and you have to multiply. For your convenience, you can write this and again write the same thing here, but put a transpose on everybody, and then do like two polynomial multiplication like that. But I will not go to that go down to that level. So, here one term, first term will be what? E is always there, delta I into delta prime n, that is delta prime n, and below delta prime transpose. Please get used to this. When I have transpose of this, I into delta prime n, that is delta prime n only, that transpose. If you are not understanding, let me write down the 2 terms. This will only become, instead of putting in bracket, for your convenience I am throwing out the bracket. So, I into delta prime n, that will become minus mu this into this and this. This one term, another I want delta prime transpose, right? With this transpose, I am doing like a, the way things are done in school. Take this, take its transpose. If you take the transpose of this, if you take the transpose of this is a vector, this is a matrix. So, this will come first, okay, and then transpose of this, but this is symmetric. Can you see? Any vector into its transpose is a symmetric matrix. Any vector x transpose, y transpose, z transpose, they are all symmetric matrices, Hermitian matrices. So, transpose is same. Otherwise, you can verify. Take the transpose of this. This comes first, transpose, transpose, cancels like that. Okay, so it remains as it is. And the other one is mu, because this is a scalar, you can write EON times this transpose or this transpose times EON, either way same. Okay. Sorry, there is a transpose here. Now we multiply the two. What we are doing after all? This vector into its transpose, and then E over that, right? So this vector into transpose, E over that. Now let's work like schoolboy. This into this, this into this, this into this, then this into this, this into this, this into this, then this into this, like that. 9 terms. Now you understand that first term will be this into its transpose, and that will be what? Simply first term will be this k prime n only, isn't it? But there are plenty other terms. Then next is this. Is this visible? This blue color visible, because other day there was some problem. Then I can multiplex actually. And then next one is minus mu E this part into this. But we assumed what is delta n? Delta n is W n minus W opt, and x prime n is obtained from x n directly, T transpose times x n. So, I assumed in that independent assumption that W n is independent of x n, and therefore, delta n is independent of x n, and therefore, delta n is independent of x prime n also. Well, x prime n is just obtained from x n, nothing else. So, that means this is one matrix. Did you understand it in the previous class? If you really, this is a matrix. This is a matrix. If you really multiply two matrices, apply E over it, you can unscramble. You can separate out the terms involving x prime, separate the terms involving this. So, instead of doing that at the end, you can as well apply E over this, and then multiply. You will get the same result. I think you can foresee that, isn't it? So, if you do that now, so these are the things I have made you prepared actually. So, that is why these things will not take much time. This will be nothing but E over this part, E over this part, right? E over this part is the covariance matrix of x prime n, but that is a diagonal matrix D. Mu D, and E over this is nothing but k prime n, and then the other one mu x prime n E O n this. If you permit, I can write E O n in the beginning, then x prime n, then this transpose. Now, you understand x prime n is independent, statistically independent with delta prime, right? E O n, that also is independent, because E O n consists of what? D n minus W opt times again x n vector. So, it depends on D n and x n vector. By my assumption, delta n and therefore, delta prime n, they are independent of D n and, do you follow? Delta n and therefore, delta prime n, because delta prime n is purely obtainable from delta n and vice versa. So, delta n and therefore, delta prime n by assumption, independent assumption, they are independent of what? X prime n, x n and therefore, x prime n and E O n, because E O n depends on D n and x prime n again, x n again. So, that means you can separate out this part E over this, E over this. Now, what is this quantity? E O n is the optimal error, and x prime n is T transpose x n. So, this quantity you can write as E, you can write T transpose out minus mu, T transpose you can take out, EON is a scalar only. This is T transpose Xn. EON you can push on the right hand side. T transpose Xn into EON. EON is a scalar. T transpose you take out. Times this quantity. Okay. But EON is orthogonal to all the components of Xn because EON is the optimal error. So, correlation is 0. So, this will give rise to 0. Please understand, it is not my purpose only to present this thing in the adaptive filter context. You will learn this term, how to carry out some statistical analysis, how to make some clever assumption here and there. This is the main purpose of this course. Okay, it is not a course on probability statistics, but it is a course which will give you some training for statistical analysis of signal and system. That is the main, that will be the main gain of this course, from this course, not to study just adaptive filters. Okay, this part is 0. So, 3 terms gone. I am left with only 6. So, next will be, so this fellow is gone. Next is this guy, delta prime n with this with this with this, right. So, this again delta prime and delta prime transpose x prime transpose E over that. You can apply E over this part separately, this part separately, very much like this. Here x prime is on the first side, delta prime on the second side, then the other way. So, I write the next term, because I am shifting this page, but you have to trust me. I will just draw, from there only. Okay, you can check in with your notes also. So, then next term is minus mu okay. Obviously, you can work on this part, you can work on this part will give you a diagonal matrix T, this will give you k prime n. So, this is minus mu k prime n diagonal D. So far so good. This term, this is a huge term, the biggest, and this we have to do separately. This again need a special this into this. I am writing it. Will be mu square minus plus mu square E. It is not difficult to remember. X prime transpose delta prime n delta prime transpose n, and again this thing comes back x prime n x prime transpose. So, not difficult to remember, only thing it requires too much of space to be written. This quantity to be done later. I will do it separately. It needs for some other steps and all that. Okay. And the last one is between these two. So, again minus plus will be mu square mu square okay. Now, this will be 0, obviously you can see. We have already done it somewhere here, same thing. Am I getting correct? No. Sorry, this will not come. This and this I have already taken care. I was by mistake I was writing it back again, so that is wrong. This with itself, this one mu square. Okay, sorry. Yeah. See how tricky it is. Even I am getting confused. Here again it is very difficult to analyze, that is where Gaussian assumption will come. By the way, I have told you one thing, that if a set of variables are uncorrelated, it is not guaranteed that they are statistically independent, but if they are statistically independent, they are always uncorrelated. But in one case only, one mean the other and vice versa, that is when the density is Gaussian. A set of Gaussian random variables, if uncorrelated, mean they are also statistically independent and vice versa. Okay, remember that. Another thing, here you see delta prime n and x prime n, by our independent assumption, they are statistically independent, right? But so these are statistically independent, because x prime n is obtained from x n and this depends only on w n. So, these two are independent. Similarly, E O n and delta prime transpose, they are statistically independent. Okay. Because U n consists of d n and x n and it consists of delta n, w n, so independent. But I do not have only this. If I had only this much like before, I could have just separated out, and by using orthogonality, this could be 0. I am getting x prime n back here again. X prime n consists of x n, E O n depends on x n. So, these two are not, at least there is some relation between them, isn't it? And then x prime n comes back here, all that. So, I cannot apply that. Here again, I will apply this again. This is all, I mean, tricks. I will apply that Gaussian thing. Now, you see, E O n, can I write this way? E O n as this vector, if I form a joint thing, W opt is a row vector, column vector, W of transpose is a row vector minus sign. These are not given in books, by the way. Book again copied from somebody else, so these details have not been spoken about in the books. First, see the first row, 1 into d n minus, this is a row vector, W of transpose x n minus of that will be a O n, no problem with that. And then I have got a 0 0 0, 0 vector as a first column, and then this submatrix is T transpose. Then can I not get this? This 0, every 0 here will take care of d n, d n will have no effect, it will be multiplied by 0 from this column of zeros. So, we will left with T transpose times x n, that will give you x prime n by our definition. So, this vector of how many? X prime consists of n plus 1 and one more, n plus 2 number of random variables, capital N plus 2 number of random variables is obtained from another vector of n plus 2 number of random variables by a linear transformation. This is a matrix only, but I assumed these elements to be Gaussian, jointly Gaussian. That was the third assumption I made. Independence assumption 1, 2, and then third assumption that the d n and elements of x n vector, they are jointly Gaussian. And from this vector, by linear transformation, I am getting another vector. So, that means they are also jointly Gaussian. Okay. This implies E 0 n and elements of jointly Gaussian. But we have also seen because of orthogonally that optimal error, we have also seen that E, can you see this in the screen? Okay, E 0 n times x prime n, all the components, if you take E 0 n and multiply with each component, take expected value, you get 0, because after all x prime n was T transpose x n, T transpose you can take out, E O n is orthogonal to all the components of x n, so 0. So, now you see you have got this situation where E O n and the other elements of x prime n, they are jointly Gaussian, but correlation between E O n and the elements of x prime n, that is 0. That means they are statistically independent, Gaussian and uncorrelated. E O n correlation with all elements of x prime n, E O n with the first element, E O n with the second element, E O n with the third element, each correlation is 0. but they are jointly Gaussian. Okay. That means they are statistically independent. You remember how we did that? We took that joint Gaussian formula, then the cross correlation terms in that matrix sigma was put to be 0, then the entire density was separable as a product of individual densities. Same thing will work here, that EON, the term from coming from EON, that can be separated out, one density term will come out. Can you see what I am saying? You will have a joint density, you have a correlation matrix in the overall joint density that will have correlation between EON and the elements of x prime n, and also their individual correlations. But those terms will be 0, EON with the correlation terms involving EON and terms from the x prime n vector. So, one probability density involving EON, that can be separated out. So, that is why the statistical independence will come up. But anyway, we have proved this result, you have to just quote this, take this result as it is, that they are jointly Gaussian, EON and the elements, they are from a jointly Gaussian set of variables. But in that, EON is uncorrelated with the rest. So, that means EON is statistically independent with the rest. So, that means EON, let me write separate here. This means EON and x prime n, they are SI, statistically independent. If so, that will help me in resolving this. So, EON is statistically independent of x prime n and of this guy, with this guy because of independence assumption, and with this guy because of this fact. So, then EON can be separated out from the rest. So, this entire E business is E over EON into E over the rest. Now, EON, what is the mean value of that? 0, because x n is 0 mean, dn is 0 mean. So, dn minus w of transpose times x n, that is 0 mean. Input x n is 0 mean, dn is 0 mean, isn't it? So, dn minus w of transpose x n vector, if you take it and apply E over it, it will be 0. E of dn is 0, E of x n is 0. Do you follow this? So, that means this will be equal to 0, because I am not writing that step. Shall I do I write the same step separately, that this E is nothing but E of EON times, that is this times this separately, and this part is 0, this part is equal to 0. This becomes E over this and E over this. How? Because EON is statistically independent of x prime n also, and by independence assumption is already independent of delta prime n, right. So, EON can be separated out, and expected value of EON is 0, because EON is what after all? dn minus w of transpose x n vector. If you apply expected value over it, E of dn is 0, dn is 0 mean, E of x n vector is 0, because x n is 0 mean, right. So, it is 0 mean, which means this is 0. So, understand, to I mean eliminate these terms, we kind of bring in this some Gaussian distribution and some assumption and all, and play around. These are the things, you are getting a training actually, to invoke as and when required, and the Gaussian assumption works very well in practice most often. Okay, so, this term is 0, right. What was this term? This was, okay, this cross middle term into middle term, that is the biggest one, and this cross term. So, I am left with only this guy with this. So, 3 more terms. They are very easily done. Delta prime n and this, that will be 0, can you see? Delta prime n independent of EON and this. So, and E over this, EON is orthogonal to the components of this x prime n, that will be 0. I will write down what I am telling you. These have to do separately, these have to do separately. Here x prime transpose delta prime, x prime transpose EON separate. So, EON is there, x prime n is there, again x prime n is there, again x prime n is there, delta prime there. So, again I will use this assumption, that EON itself is independent of x prime n also, delta prime n also. So, EON part can be separated out, E of EON will come separately, which is 0. Okay. Are you following? That same thing, this part I will use here also, where when I handle this product, these two will involve EON. EON is a scalar, EON you write on the right hand side, and rest x prime transpose this, the one hand. EON is independent of that. So EON can be separated out, expected value of EON, that is 0. So that term will go. I am left with only this. So I am writing down the terms quickly. Next class I will not redo this. So we need to collect these terms. Maybe I will take these pages with me. And so another term is minus mu E of delta prime n this is 0 obviously, no? Because this you can separate out with this and this, because of orthogonality will go. I am repeating what I stated, and that other term is plus, because minus plus mu square E but here you assume that here you make the make use of the fact that this fellow is independent of the rest. So, E over this will come out separately, which is 0. So, this will go to 0. The only thing is last term is important. Last term is product of these two, minus plus mu square x prime square, there is x prime n transpose, and E0 n this is scalar E0 square. So, plus mu square E of E0 square n and E0 n x prime n, they are statistically independent, we have said, and therefore E0 square is statistically independent of this. That is the advantage of statistical independence. Now, if x and y are independent, then x square, y cube, fx, gy, they are all independent. So, that means this part is independent of this part. So, you can separate out expected value of U square n is the epsilon square mean, that is the minimum variance attainable, because this is optimal error. So, mu square, because EON, when you have put the optimal filter, the corresponding variance is the minimum attainable, this, and E of this is your D. Okay, so, in the next class I will start from here. Remember, we did not work out this particular term. Okay, what term? I left us to be done later. And where is that page? Yeah, this one, to be done later. This did some special analysis, not very big, but again some fact of Gaussian distributed variables. That if 4 variables are there, x1, x2, x3, x4, and there is a product x1 into x2 into x3 into x4, and take E over that. Under the Gaussian case, you can simplify it at E of x1, x2 into E of x2, x3, x4 plus E of x1, x3 into E of x2, x4 plus E of x1, x4 into E of x2, x3. This kind of permutation, that fact has to be used there to simplify. So, I will do that in the next class. Okay? Thank you very much.